Did you know that black holes are so dense that nothing, not even light, can escape their gravitational pull? Welcome to our deep dive into the mysteries of black holes. Black holes, these enigmatic entities of the universe, are regions of space-time where gravity is so strong that nothing, absolutely nothing, can escape from it. They are formed when massive stars collapse under their own gravitational pull, creating a point in space where gravity is so intense that it warps the fabric of space-time itself. Now, black holes come in two main flavors: stellar mass and supermassive black holes. Stellar mass black holes, as their name suggests, have masses ranging from about 5 to several tens of times the mass of our Sun. They are usually found scattered throughout the galaxy, often lurking quietly until some unsuspecting gas or star comes along. On the other hand, supermassive black holes, well, they're a different beast altogether. These behemoths have masses millions or even billions of times that of our Sun. They reside at the centers of galaxies, including our own Milky Way, and they have a knack for causing cosmic commotion. Interestingly, these two types of black holes feed in different ways. Stellar mass black holes often dine alone, occasionally tearing apart a passing star. Supermassive black holes, however, are the cosmic equivalent of banquet hosts. They're surrounded by vast amounts of gas and dust, forming what's known as an accretion disk. This accretion disk is a swirling maelstrom of matter, spiraling inward toward the black hole. As this material gets closer to the black hole, it heats up and emits radiation, making the disk glow brightly. This is how we can detect and study these otherwise invisible entities. As we delve deeper into the nature of black holes, we'll see that their unique properties give rise to some fascinating phenomena. Imagine a black hole at dinner time. How does it eat? Let's explore. When a black hole is ready to feast, it doesn't use a knife and fork. Its dinner plate is an accretion disk, a swirling vortex of gas, dust, and other interstellar material. As objects get sucked into the black hole's gravitational pull, they don't fall straight in. Instead, they spiral inwards, a dance choreographed by the conservation of angular momentum. Picture a figure skater. As she pulls her arms in, she spins faster. The same principle applies to material falling into a black hole. As it gets closer, it spins faster, creating a flat, circular disk. This is the birth of the accretion disk, a hotbed of cosmic activity, heated to incredible temperatures by the friction of material jostling for space. Now, the physics of an accretion disk is a symphony of complex processes. Radiation mechanisms play a key role. As the material in the disk heats up, it emits radiation, light across the electromagnetic spectrum. This is why we can see quasars, the bright centers of distant galaxies, where supermassive black holes are chowing down on copious amounts of material. Viscosity, the measure of a fluid's resistance to flow, also plays a part in this cosmic banquet. It allows material to lose angular momentum and spiral inward, feeding the black hole. It's like the syrup slowly dripping off your morning pancakes. Then, there are instabilities. Sometimes the inward and outward forces within the disk can become unbalanced, causing the disk to wobble or warp. These instabilities can lead to dramatic outbursts of light, adding a touch of drama to the black hole's mealtime. The world of accretion disks is a swirling, chaotic, and incredibly hot environment. It's a place where the usual laws of the universe seem to bend and twist, where matter is consumed, and energy is spewed out in a spectacular display. These swirling disks of cosmic material are not just a feast for black holes, but also a powerhouse of energy, emitting light across the electromagnetic spectrum. Accretion disks can be in a low luminosity state or a high luminosity state, each with its unique characteristics. Now, let's delve into the world of low luminosity and high luminosity accretion states. Picture an accretion disk, a swirling, hot, turbulent ring of gas and dust around a black hole. Depending on the amount of matter it's consuming and the rate at which it's eating, the disk can find itself in one of two states. First, we have the low luminosity accretion state, or LLAS. This is when the black hole is dining at a leisurely pace, not consuming much matter. The disk's radiation is predominantly hard X-rays, with a weaker, soft X-ray component. The disk is dim, relatively cool, and the matter within it moves in a more or less orderly manner. Contrast this with the high luminosity accretion state, or HLAS. Here, the black hole is in a feeding frenzy, gobbling up matter at a high rate. The disk is brighter, hotter, and more chaotic. Radiation is dominated by soft X-rays with a lesser hard X-ray component. The disk's structure is also more unstable, with larger fluctuations and more turbulence. These different states don't just influence the disk's luminosity. They also affect the energy output and observational signatures of black holes. For instance, in the HLAS, the larger energy output can lead to more powerful jets, streams of particles shooting out from the black hole's poles at nearly the speed of light. But what causes these shifts between states? The answer lies in the spin of the black hole itself. A spinning black hole can drag the space-time around it, a phenomenon known as frame dragging. This can influence the disk's structure, causing it to transition between the LLS and HLAS. The spin of a black hole plays a crucial role in these accretion states and in the formation of something even more fascinating: jets. Emanating from the poles of some black holes are jets of energetic particles, traveling at nearly the speed of light. These are no ordinary jets. They're cosmic powerhouses, spewing out vast amounts of energy into the cosmos. But how did we come to know about these fascinating phenomena? Well, it all began with the discovery of radio jets and later blazars. These are different types of jets, each exhibiting unique behaviors and characteristics. For instance, radio jets were found to have a distinct morphology, showing variability and incredible energetics. On the other hand, blazars captivated us with their spectacularly bright and variable emissions, a testament to the immense power of black holes. Now, you might wonder, how are these jets launched? It's a question that has puzzled scientists for decades. Current theoretical models suggest that these jets are formed through a process known as magnetohydrodynamics, or MHD for short. This process involves the interaction of magnetic fields with electrically conducting fluids, such as the plasma found in the accretion disk around a black hole. So, what role do magnetic fields play in all of this? Well, they're the linchpin. As matter spirals into a black hole, immense magnetic fields are generated. These fields interact with the rotating plasma, creating a twisting force that propels matter outwards in the form of jets. Think of it like a cosmic slingshot, flinging energetic particles into space at near light speeds. But these jets aren't just fascinating to study. They also have profound impacts. They can influence the interstellar medium, the stuff between the stars, and even impact the evolution of galaxies. Yes, these jets of energetic particles launched by the ferocious power of black holes can shape the very structure of the universe. In essence, we're talking about one of the most powerful and fascinating phenomena in the cosmos, a testament to the wild, energetic, and often surprising nature of our universe. These jets are not just a spectacle, but also have profound impacts on their surrounding environment. Black hole jets can alter galaxies. Let's explore how. These jets are not just visually impressive. They play a significant role in shaping the universe around them. As they burst out of the black hole's gravitational clutches, they interact with the interstellar medium. The space between the stars filled with gas, dust, and stray cosmic rays. These interactions can be quite dramatic. The jets, traveling at near light speed, create shockwaves in the interstellar medium, heating it and creating cavities of hot gas. This process, known as radio mode feedback, can have a profound impact on the host galaxy. It can halt star formation by heating and dispersing the cold gas clouds where stars are born, thus changing the galaxy's evolution. But the story doesn't end there. This feedback loop between black holes and their host galaxies is a two-way street. The energy from the jets can also compress the surrounding gas, sparking new star formation in a process known as positive feedback. So, in a strange way, black holes, known for their destructive power, can also be creators, contributing to the very life cycle of the universe. And the influence of black holes extends even further. The outflow of energy from the jets can reach into the larger scale structures of the universe, into clusters of galaxies, and even into the vast cosmic web that connects all matter in the universe. This is called AGN feedback. where AGN stands for active galactic nuclei, the active jet-producing black holes at the heart of galaxies. These feedback processes are critical for understanding the coevolution of galaxies and their central black holes. They help explain why galaxies and their black holes grow together, why large galaxies host larger black holes, and why some galaxies stop forming stars. Despite all we know, there are still many mysteries surrounding black holes and their jets. We are just beginning to unravel the complex interactions between black holes, their jets, and the cosmos at large. And every discovery brings us one step closer to understanding our place in this vast, ever-changing universe. The study of black holes and their jets is a thriving field in astrophysics, with many open questions to answer. We've come a long way, but there's still much to learn about these cosmic mysteries. As we speak, scientists are using a multitude of observational techniques to unravel the secrets of black holes. Across the globe, observatories are tracking the radiation signatures of black holes, from low-energy radio waves to high-energy gamma rays. This multi-wavelength approach is vital, as it allows us to probe different aspects of black hole accretion and jet formation. In addition, we're looking forward to the next generation of telescopes. The Square Kilometre Array, for instance, will be the world's largest radio telescope and promises to revolutionize our understanding of black hole jets. Its unprecedented sensitivity and resolution will allow us to study jets in more detail than ever before. Meanwhile, projects like the Event Horizon Telescope are pushing the boundaries of what's possible, producing the first ever image of a black hole's event horizon. And this is just the beginning. Future missions, such as the proposed Black Hole Imager, aim to directly image the accretion flow and jet launching region of a black hole, something that's never been done before. But it's not just about observation. Theoretical studies are equally important. Researchers are using advanced computer simulations to model the complex physics of black holes and their jets. These simulations help us interpret observational data and test our theories. In essence, the future of black hole research is about synergy. It's about combining observations across the electromagnetic spectrum, harnessing the power of next-generation telescopes, and integrating these with theoretical models. This multifaceted approach is our best bet to answer the big questions. How do black holes feed? How do they launch jets? And what impact do they have on their surroundings? As we continue to study these cosmic behemoths, we might just uncover more about the fabric of our universe. So what do you think? How might black holes reshape our understanding of the universe?